Have you ever wondered about temperature? How hot can things get? Is there any limit to how hot something can become, or is it infinite? Just keep adding energy and things will continuously get hotter. Did you know that the sun's core can reach millions of degrees Celsius? Some stars even burn at billions of degrees. Does this mean there's no maximum temperature, no upper limit at all? But what about the cold side? How cold can things get? Are you thinking that the same rule applies, that there's no limit to how cold something can get, just as there's no limit to how hot it can get? Colder and colder and colder forever? Absolutely not. In reality, there's an ultimate point, an absolute threshold, a temperature that you simply cannot go beyond, no matter how hard you try. We call it absolute zero, minus 273.05 degrees Celsius, minus 459.67 degrees Fahrenheit, or simply zero on the Kelvin scale. But what makes this difference? Why is there a coldest possible temperature, yet no hottest? So what makes cold completely different from heat? And what actually happens at absolute zero? Does all motion completely stop? The answer will reveal a profound truth about the true nature of temperature. And once you understand this, the existence of absolute zero will not only become obvious, but also inevitable. First, let's set aside everything you thought you knew about temperature. It's not simply the feeling of hot or cold from an object. After all, that's a subjective experience, completely meaningless in the realm of physics. So what is temperature really? It is motion, the constant movement of atoms, of molecules. Everything around you, from this screen, the air, to your very own hand, is made up of trillions of tiny atoms. And these atoms are constantly moving, vibrating, oscillating, colliding non-stop. In a solid state, atoms simply vibrate in place. Fixed within a crystal structure, they vibrate faster as temperature increases and slow down as temperature decreases. What about in a liquid? Atoms slide past each other, still constantly moving, still oscillating, but now they can flow freely. In a gaseous state, atoms fly around completely freely, constantly colliding with each other and bouncing off the walls of their container. Did you know that the air we breathe, with its nitrogen and oxygen molecules, is moving at hundreds of meters per second? Right now, in this very room, and this is the crux of the matter, temperature is nothing more than a measure of this motion, specifically the average kinetic energy of particles. So what does hot mean? It's when atoms move fast. And cold, simply when atoms move slowly. It's that simple. That's the nature of temperature. When you heat an object, you are essentially adding energy, causing its atoms to move faster. Conversely, when you cool an object, you are taking away energy, causing its atoms to slow down. Have you spotted the problem yet? How cold can we make an object? You remove energy, the atoms slow down. Continue to remove more energy, and they'll slow down even further. But is there a limit to the slowest speed they can reach? The answer is zero. Atoms cannot move slower than being completely still. They cannot possess a negative speed. Therefore, motion always has a minimum value, that is, zero velocity. And because temperature is a measure of the average kinetic energy of atomic motion, is that why there's a minimum temperature? Exactly, the temperature at which the motion of atoms reaches its minimum possible value, that is absolute zero. It's not a random number, nor is it a practical limit imposed by our cooling technology. Instead, it's a fundamental limit. It's deeply integrated into the very nature of motion itself. You cannot achieve a speed below zero. So how could you possibly go below zero temperature? It's that simple. That's the explanation. Motion has a minimum value, and therefore temperature must also have a minimum value. Things are about to get really interesting. Did I just say that atoms completely stop moving at absolute zero? That's almost true, but is it the whole truth? The reason behind it reveals a deeper secret about the universe, quantum mechanics. In Newton's classical world of physics, we can easily imagine atoms completely motionless, without any movement, no energy, just frozen in place. But is that true? Quantum mechanics completely refutes it. Why? Because there's a key principle called the Heisenberg uncertainty principle. This principle states that we cannot simultaneously determine both the precise position and momentum of a particle. So what would happen if an atom were completely still, with both its velocity and momentum equal to zero? Wouldn't we then know its momentum is exactly zero? And if it just stayed in one place, wouldn't we also know its exact position? But is that allowed? Absolutely not. Because this would directly violate the uncertainty principle. Would nature tolerate such a contradiction? So even at absolute zero, do atoms truly become completely motionless? Not at all. They are forced to maintain a minimum amount of motion, an irreducible jiggle. We call this zero-point energy. This is the lowest energy state a system can achieve, but is it zero energy? Absolutely not. That's the minimum threshold that quantum mechanics allows to exist. And this also explains a strange phenomenon. Why does liquid helium never freeze into a solid at normal pressure, even at absolute zero? Because their zero-point motion is too great. The atoms jiggle so violently that they cannot lock into a crystal lattice. They remain in a liquid state, a unique quantum fluid, even when the temperature has dropped to the coldest possible level. Is there anything more astonishing than that? If motion never completely stops, then what truly happens as we approach absolute zero? Is it just stillness? No. That's when strange, beautiful phenomena begin to reveal the deep quantum nature of reality. Normally, gas condenses into a liquid, and then the liquid freezes into a solid. That's pretty familiar, right? But if you keep cooling, bringing a gas down to just a few millionths of a degree above absolute zero, what unexpected thing will happen? An incredibly strange phenomenon will appear. That gas will turn into a Bose-Einstein condensate. Can you imagine? At normal temperatures, gas atoms fly around freely, each in its own direction, at its own distinct speed. A constant chaos, right? But as we approach absolute zero, will order be established? Something truly astonishing will happen. How much do the atoms slow down? To the point where their quantum wave functions begin to overlap. And when that happens, are they still individual entities? No, they stop acting independently. They merge into one, a single quantum entity. Can you imagine? Thousands, even millions of atoms acting together as one single, perfectly coherent quantum object. Imagine a room full of people dancing randomly, and then suddenly they all synchronize into a single, perfectly choreographed movement, all moving together, all doing exactly the same thing. This is a completely new state of matter, not a solid, liquid, or gas. So what is it? It's something entirely different, a macroscopic quantum state, large enough for us to see with our naked eyes, yet operating under quantum rules. Does that make you think? Quantum mechanics usually only governs extremely tiny things, electrons, photons, or individual atoms. But here you can witness it firsthand, a blob of matter the size of a grain of sand acting as a single quantum object. Is there anything more astonishing than that? And does it do strange things? Absolutely. Superfluidity will appear. Liquid helium will turn into a superfluid, can you believe it? Below about 2 Kelvin, it flows without any friction, without any viscosity. It can climb up the sides of its container and spill out on its own. Can any other liquid do that? It can also flow through holes so tiny that normal liquids could never pass through. Why is that? Because friction requires energy dissipation, which only happens when atoms collide and lose energy. But a superfluid is a single quantum state. Is there any mechanism for it to lose energy? Absolutely not. No friction? Can a liquid flow perfectly forever? Try putting it in a container, spinning it, and will that liquid really just keep spinning endlessly? Never slowing down, never stopping, because there's nothing to impede it. This is where superconductivity comes in. Some metals, when cooled below a critical temperature, suddenly lose all electrical resistance. What happened? Can an electric current flow forever without energy loss, without generating heat? Try running a current through a superconducting loop. Will it really circulate perpetually? For years, even decades, no power source, no battery, it just keeps flowing. Why? Because there's no resistance to dissipate energy. And here's another quantum mechanics mystery. Electrons pair up, forming a coherent quantum state. What does this mean? They flow together as a single entity, no scattering, no resistance. Are these just tiny effects? Not at all. They are macroscopic quantum phenomena, clear evidence that quantum mechanics isn't just limited to subatomic particles. So what else does it govern? It governs the behavior of matter at the coldest temperatures. And here's another strange fact. You can get incredibly close to absolute zero, extremely close, but can you ever actually reach it? Scientists have cooled atoms to billions of a degree above 0 nanokelvin, almost touching it, but why can't we ever truly reach it? Why is it impossible? It's due to thermodynamics, specifically the third law. Cooling an object requires removing energy, and to remove energy you need something colder to absorb it, a heat sink. But what if there's nothing colder? But if you're already at the coldest possible temperature, where does the energy go? Is there a colder reservoir to absorb it? You can't remove that last bit of energy. Every cooling method brings you closer, but does each step require more effort, more energy, more time? And the closer you get to absolute zero, does it become harder to go further? It's an asymptote. You approach it, get arbitrarily close, but can you ever truly touch it? This isn't a technological limitation. We're not just waiting for better refrigerators. No, it's a fundamental principle built into the laws of thermodynamics. What does this mean? Nature won't allow you to reach absolute zero, not because it's difficult, but because it's impossible. So why does absolute zero exist, and what is its significance? While there's no maximum temperature, because temperature measures motion, and motion has a natural 0 point, you can't move slower than not moving, but is there an upper limit to motion? You can always move faster, add more energy, the temperature will be higher. The sun is millions of degrees. Supernovae are billions. Is there a limit to this heating? Particle colliders create temperatures of trillions of degrees, far exceeding the sun's core. So there's no upper limit, but there is a hard limit at the bottom. Why this difference? Actually, there might be a maximum temperature. The Planck temperature is about 10 to the 32nd Kelvin. What would happen at this terrifying temperature? Above this level, our current physics completely breaks down. Space and time themselves become uncertain. Quantum gravity dominates. Can we even imagine what would happen? But that's a different kind of limit, a limit of our theories, not necessarily of nature itself. Absolute zero is different. It's real, fundamental, unavoidable. Why is it so absolute? And the closer you get to it, the more quantum mechanics dominates. The classical image of bouncing balls fails more and more, and you see the true quantum nature of matter more clearly. Are there mysteries waiting to be discovered? Hot objects are easy to visualize. Atoms colliding like billiard balls, everything predictable, right? But what about cold objects? They obey quantum mechanics, where wave functions overlap and particles act collectively. Is it a completely different world? Friction suddenly vanishes and electrical resistance disappears without a trace. What happens when the temperature reaches the coldest possible point? Do quantum effects completely take over, dominating everything? Do particles merely slow down when reaching absolute zero? Or do they reveal a completely different nature? Not tiny spheres, nor miniature planets, but quantum entities, mysterious wave-like probability distributions, right? Entities can coexist in a single state, acting as a unified whole. So why can nothing be colder than absolute zero? Is it because we lack the technology to create better refrigerators, or because the very nature of cold is the slowing down of atomic motion? Motion has a minimum limit of zero, but quantum mechanics adds a small, irreducible vibration. Is this random or merely a limit of our technology, or is it an inevitable consequence of the true nature of temperature? Isn't temperature simply a measure of motion, and doesn't motion have a fundamental limit? When you truly understand this, is absolute zero still a mystery, or does it become an inevitability, a beauty deeply connected to the quantum nature of the very reality we live in?